Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about simple linear regression, where we want to estimate a certain quantity of interest as a linear function of another quantity of interest. We're going to see that this problem is intimately related to correlation. Let's get to it. We're going to talk about simple linear regression. In general, the problem of regression is that of estimating a certain quantity of interest that we're going to call the response from observed variables that we call features. In the case of simple linear regression, we only have a single feature, a single observed variable, and we constrain our estimate of the response to be an affine function of the feature. We model both the feature and the response as random variables so that this constraint looks as follows. We want to approximate the response, which is this random variable b, and we constrain the estimate to be a scaled version of a, of the feature a, plus some constant. Okay, so there's a constant scaling and then an additive constant. Our plan in this video is to derive the optimal linear estimator, so what is the optimal scaling of the optimal additive constant, to explain how to estimate them from data, and to compare this linear estimator to a nonlinear estimator. To begin, it will be useful to remind ourselves what a standardized variable is. A standardized random variable is a random variable from which we have subtracted the mean and which we have divided by the standard deviation. What do we achieve by this? Well, we center the random variable. The mean of the standardized variable is going to be equal to 0, and we normalize it so that the variance of the standardized random variable is equal to 1. In a previous video, we proved that the best possible linear approximation of a standardized random variable s of b given a standardized random variable s of a is just scaling by the correlation coefficient between the standardized random variables, which is just the mean of their product. This immediately gives us a way of estimating the response, which is b, in terms of the feature, which is a. So before we hadn't interpreted linear dependence between random variables in this way. Now we're interested in estimating b from a. So how can we use this information that we have? Well, we can express the response in terms of its standardized variable by just multiplying by the standard deviation and adding back the mean. And now we know how to estimate the standardized response. We just multiply the standardized feature by the correlation coefficient between the standardized response and the standardized feature. When we plug that in, we get an estimator of the response given the feature, because what is this standardized feature is just the feature minus its mean divided by the standard deviation. This affine estimator, as we will see in a moment, happens to be optimal from the point of view of mean squared error. But before proving that, I want us to gain some intuition about this seemingly complicated function that we have come up with. In order to do that, we're going to look at an example. So here on the left, I'm showing you the standardized, basically samples from the two standardized random variables. And we see the linear estimator, which is obtained by just multiplying s of a times a constant, which is the correlation coefficient between s of a and s of b. That correlation coefficient tells you to what extent they're linearly dependent. But now what happens if what we actually want to estimate is b and not the standardized version of b from a, not from the standardized version of a? Well, if a has non-zero mean and standard deviation which is not equal to 1, we're going to have to correct for that to obtain a line that actually goes through the data. So this is what the data look like. In order to obtain this line that actually goes through the data, well, we have to incorporate the mean and the standard deviation so that the line is shifted and actually goes through the data. This is what these terms achieve. Now imagine that the response is the one that has non-zero mean and a standard deviation that is not equal to 1. We have to account for that if we want to transform the estimate of the standardized variable into an estimate of the actual response. How do we do that? Well, by adding the mean and scaling by the standard deviation, and then indeed we get a line that goes through the data points. Now, if we put everything together, what happens if the means are non-zero and the standard deviations are not equal to 1? We will have to correct for that, and the expression we derived is exactly the way to correct for that, so that the line goes through the samples of the non-standardized variables. Okay, so hopefully this gives you some visual intuition about this function that we have derived. Okay, so now let's take a step back and say, okay, imagine that we didn't know about correlation coefficients. What if we want to directly just find the affine estimate that is best in terms of mean squared error? So we want to find the best scaling and the best additive constant that allow us to approximate the response from the feature. Well, let's do it. Our strategy, maybe let me tell you about the general strategy beforehand. We're going to first determine what the optimal alpha is in terms of beta, and then we will optimize with respect to beta. That's what we're going to do. A useful result that we had established when we talked about the mean squared error is that if you want to estimate a certain random variable using just a constant, and you want the best estimator in terms of mean squared error, then that best estimator happens to be the mean. We already proved this in the video about the mean square in particular, the video about variance and mean square. Basically what you do is you expand this thing and you minimize with respect to c by taking derivatives, in case you don't remember. Why is this useful? Because now when we look at alpha, we can actually find the optimal alpha for any value of beta, which we denote by that. What is alpha doing here? Well, alpha is essentially a constant estimate of b minus beta a. You can call this a random variable x. What is the best constant estimate of x given, that's it, given nothing? What is the best constant estimate of x? It's its mean. So we can directly set alpha equal to the mean of b minus beta a, which is just equal to the mean of b minus beta times the mean of a. Now this is the optimal alpha for any value of beta as a function of beta. So we want to minimize the mean squared error with respect to beta. We can just plug in that value of alpha because we know that you cannot achieve a smaller value of a smaller MSE for that particular value of beta. So now we're going to plug it in and minimize with respect to beta. So we plug in the expression that we know for the optimal alpha, and now we're going to expand this mean squared error. We're going to expand it by grouping b with its mean and grouping beta a with its mean. Okay, so we're going to take the square of b minus its mean square, so the square of b minus its mean, and then by linearity of expectation we can just take that out as this term. Then beta comes out by linearity of expectation, and we have the mean of a minus its mean squared. And then we have this cross term that is the mean of the product between the centered feature and the centered response. Now, what are these values? Well, you know very well what these values are. Just by definition, this is the variance of b, variance of a, covariance of a and b. So we have a very nice expression. The MSE actually only depends on the variances and the covariance between the two random variables. That's all it depends on. So now we want to find the best beta. What do? We minimize this expression as a function of beta. We find the derivatives. We take the first derivative. This is easy, right? Because here we just have beta squared. Derivative is 2 beta. The derivative of beta is just 1. And then we have to multiply by whatever constants are multiplying them. So this is the first derivative. The second derivative is actually just equal to 2 times the variance of a, which is non-negative. We're going to assume that the feature has non-zero variance because otherwise it's just equal to a constant. It's not a very interesting feature. In that case, the mean squared error is convex with respect to beta, right? So it looks like this. And we can just look for the minimum by setting this first derivative to 0. That gives us a value of beta that is equal to the covariance divided by the squared standard deviation of a, the variance of a. Remember that the correlation coefficient is equal to the covariance divided by the product of the standard deviation. So this is just equal to the correlation coefficient times the standard deviation of B divided by the standard deviation of A. So now, if we plug in the optimal value of alpha corresponding to this value of beta, we get this expression for the optimal affine estimator of B given A, which is exactly the same as what we obtained based on our argument based on the correlation coefficient. It's exactly the same. This shows that this is the optimal, the linear minimum mean squared error estimator. If you're a mathematician, you might be like, oh, but this is not linear, it's affine because there's a constant. But everyone calls this a linear estimator, so that's what we're going to do. Okay. So now let's do an example. Let's compute the best linear estimator of the number of cats given the number of dogs, for this example that we already looked at in a previous video. This is the joint PMF of the number of cats and dogs in different households in a fictitious city. I actually made this up. And we're going to compute the optimal linear estimator of the number of cats given the number of dogs. So if someone tells us, oh, in this house there are 2 dogs, we're going to come up with the optimal linear estimator of the number of cats. So we just need all of these values here. We need the correlation coefficient, the means, and the variances. We computed this in a previous video. The means were equal to this. The variances were equal to that. The covariance is negative. They're negatively correlated. And from the covariance, we can compute the correlation coefficient by dividing by the standard deviations. When we plug in all of these numbers, we indeed get an affine estimate of the number of cats given the number of dogs. We need to multiply the number of dogs by minus 0.3 and add this constant. That is the best linear estimate. So if someone tells us that the number of dogs is equal to 0, then our estimate for the number of cats is 0.756. If the number of dogs is 1, our estimate for the number of cats is 0.456. If the number of dogs is 2, our estimate for the number of cats is 0.156. Because the two quantities are negatively correlated, we decrease our estimate as the number of dogs increases. Let's take a look at what's the mean squared error of this estimate. How do we compute the mean squared error? Well, we compute the mean value of the true value of cats minus the estimate, which is only a function of the dogs. Okay, so here we would plug in all the possible values for C, and we subtract this value from them, and we multiply by the corresponding probability. Okay, so if we do that for all the possible values of C, here, by the way, there should be, we also need to sum over. It's incredible because I have looked at these slides over and over and over, and there's always something that escapes me. Okay, so we also need to add over the number of dogs. Okay, when we sum all of that, we get a value, an MSE that is equal to 0.759. Okay, that's the mean squared error for our linear estimator. Now we could ask ourselves, is this linear estimator optimal? Well, not necessarily. We already proved when we talked about the conditional mean that the optimal estimator in terms of MSE is the conditional mean, in this case of the number of cats given the number of dogs. So let's first of all remind ourselves, we already derived this estimator in the video on a regression using the conditional mean. Essentially what we need to do is we need to derive the conditional PMF of cats given dogs, which happens to be this one. Okay, you just need to normalize basically the joint PMF appropriately. And then using that, we compute the mean number of cats conditioned on each number of dogs. Okay, so for 0, the mean number of cats is 0.77. For 1, it's 0.4. And for 2, it's 0.29. Now we can compare this to our linear estimator. And it's actually quite similar. It's quite similar, but it's a bit different. And now we have to realize that this linear estimator is actually constrained, right? So if you imagine it as a function, maybe I should have just plotted it, but since I didn't. So let's say that this is 0, this is 0, this is 1, and this is 2. Our linear estimator is constrained to lie on a line. We're actually constrained to lie on a line. Whereas the nonlinear estimator does not necessarily lie on a line. It could be, it can depart from a line as much as it wants. So it has more flexibility, and in this case, it's different from the linear estimator. It achieves a smaller MSE. The MSE for the minimum MSE estimator given by the conditional mean is 0.76, but the linear estimator is not so bad. It's 0.79, slightly higher. So in this case, we don't pay a lot by forcing our estimate to lie on this line, but it's important to realize that if there's some nonlinear structure that cannot be accounted for by having an estimator that lies on a line, then we're not going to be able to incorporate it into our linear estimate. Okay, so in general, the nonlinear estimator is going to be better than the linear estimator, but in many cases, such as this one, the difference might not be very large. And the advantage of the linear estimator is that at the end of the day, it just depends on the correlation coefficient up to normalization and summing and so on. So we can express it with a given number, which is nice. In contrast, the conditional mean, we have to specify the conditional mean separately for each possible value of, in this case, the number of dogs, or each possible value of the feature. So there's that trade-off. Let's take a look at what happens for Gaussian random variables. So we're going to assume that the feature and the response are jointly Gaussian, which means that when we stack them up in a vector, they have a certain mean and a certain covariance, and their joint PDF is a Gaussian random variable with that mean and that covariance matrix. Now, what is the minimum MSE estimator of B given A? It's a conditional mean function, right? Exactly like what we saw here with the cats and dogs. That's the optimal nonlinear estimator, the optimal estimator. However, the conditional mean function for Gaussians, which we derived, you can go and look at the video on the marginal and conditional distributions of Gaussians. The conditional mean function in this case is exactly equal to the linear MMSE estimate of B given A. Okay, I want to be very, very clear. What is the distribution of B given A? It's a Gaussian that has this mean parameter, and hence this mean when we condition on A being this constant value. So because of that derivation that we had performed, we showed that the conditional mean function is actually an affine function of A. In this particular case, the best nonlinear estimator is exactly the same as the best linear estimator, but this only holds in general for Gaussian random variables. Okay, so here the conditional mean is actually equal to the linear MMSE estimator. This just shows that for Gaussians, dependence between Gaussians is completely linear. So we're not going to gain anything by using the nonlinear estimator. We're just going to obtain a linear function. Okay, this is in line with what we had seen in the previous video, where we saw that the correlation coefficient completely governs dependence between two random variables with zero mean and unit variance. Okay, so now how do we perform simple linear regression when we actually have data? We have been talking about random variables, but in practice, we actually have data. So we have examples of the feature, and for each example, we have an associated example of the response. How do we set up an estimate of, in this case, y given x? So just to visualize what I'm talking about, here I have a data set where we have rebounds per game associated to the height of basketball players. What if we want to estimate the rebounds based on the height? Okay, each point here is xi, yi. So xi is here and yi is here. Okay, just so that you visualize what we're talking about. So we want to estimate the response y from the feature x. So what could we do here? Well, what we can do is we can say, okay, we can interpret xi as a sample from a certain random variable and yi as a sample from a random variable representing the response. So this random variable represents the feature, this one represents the response. We know how to perform estimation between random variables. You just use the linear MMSE estimate that depends on the correlation coefficient between the random variables. Okay, it has this expression. Now, this depends on the correlation coefficient, on the standard deviation, and on the mean of the features and the response, but we can just replace everything by the corresponding sample estimates. We can plug in here the sample standard deviation, which is the square root of the sample variance of y. I should have said this, okay? But here, these elements are the, like if we create just a data set with of responses, and these are the data set of features. So this is the sample variance of the responses, and this is the sample variance of the features. Same for, this is the sample mean of the feature, and this is the sample mean of the response. So we basically replace the mean by the sample mean, the variance by the sample variance, and the correlation coefficient by the sample correlation coefficient. Another possible idea would be to say, okay, this stuff with random variables is very complicated. How about I just say, okay, I want to find a linear coefficient and an additive constant such that when I compute my squared error over my whole data set, if I compute the difference between the response and this estimate given by this multiplicative coefficient and the additive constant, that is minimum. Okay, like I minimize the sum of squared errors. Well, this is going to give you exactly the same answer. Exactly the same answer as when we use our argument that we established for random variables, and we replace the means, variances, and correlation coefficient by their sample estimates. We're not going to prove this in this video, but the proof is extremely similar to the proof that we went through with random variables, except that every time that we have an expectation operator, we have a sum instead. Otherwise, the proof is very, very similar. Okay, so now let's take a look at some actual data. We're going to again look at how the height of NBA players is related to their offensive statistics, in particular points, rebounds, assists, and points. Here, the correlation coefficient between height and rebounds, as we had seen in the previous video, is 0.42. When we construct the affine estimator corresponding to that value of the correlation coefficient using the sample variances and the sample means and so on, we obtain this estimate, which is on this line, for the rebounds, which I have put on top of the scatter plot. So you can see it as the best line that goes to the scatter plot of feature and response pairs. The correlation coefficient between height and assist is equal to 0.46 when we minus 0.46 when we construct the affine estimator corresponding to that value of the correlation coefficient. We see this line going down. That's the best linear estimate of assists given the height of a player. And this is the best linear estimate or affine estimate of the points given the height of a player, because points are not very correlated with the height. The estimate is kind of constant, close to just the mean points scored by every player. So now let's compare these estimates that we obtain from data with a nonlinear estimate. So we have said that in the case of random variables, we know what the optimal estimator is. It's the conditional mean function. So if we want to approximate that from data, what do we need to do? We have to look at each height and compute the conditional mean of the quantity of interest given that height. And that's what we're going to do, and we're going to compare it to the linear estimate. Okay, so we need to the conditional mean function of b given a. We're going to approximate it from data. This is what we obtain. The first thing to notice is that the estimate is kind of noisy, especially in areas where we don't have a lot of data. And that is normal, right? Because if you don't have a lot of data, you are estimating a mean using averages. If you don't have, this is going to be noisy. So that's a disadvantage of the nonlinear estimator. The second thing that we notice is that it's not that far apart from these noisy, you know, like these noisy elements. It's not that far from the linear estimate, but there is a difference. Here, it looks like rebounds are almost constant for small players. And we see a similar thing when we look at assists. Assists for small players are again almost constant. There's this noise, okay? And they're also almost constant for tall players. This actually makes a lot of sense because our logic for why assists and height were inversely correlated is because small players are the ones that usually pass. But Players that are smaller than 195 centimeters, almost all of them are point guards, which is the player that distributes the ball in the team. So it is actually very natural that if you condition on that, on saying, oh, I'm only going to take players that are smaller than 195 centimeters, then in general, they're all point guards. So you can't really estimate just based on height how much assists they're going to do. So it makes sense that for that, the nonlinear estimate would be approximately constant. This cannot be captured by the linear estimate because the linear estimate is constrained to be a line. It cannot be something like that. Okay, we don't allow it because we're constrained to be a line. It's the best line, and the best line kind of is close to the nonlinear estimate, but cannot account for that structure where it would be better in terms of sum of squared error to make the estimate constant for very short players or very tall players. All right, and here in points, we basically see again that the two estimates are very close, and we observe some noise in areas where we don't have a lot of data. So there's a trade-off here, right? The linear estimate gives us a very simple estimate that can be essentially summarized with a single number, which is great, right? And does not have that much noise. That's also great. So we don't see this noise when we don't have a lot of data, but it cannot capture important structure, such as the fact that assists and probably rebounds should be constant once you condition on the fact that a player is small, is short, or very tall. Okay, and that's a general trade-off that you're going to have between linear estimation and nonlinear estimation. All right, so what have we learned? We have derived the optimal linear MMSE estimator for simple linear regression. We have shown how to compute it from data, and we have compared the linear estimator to nonlinear estimator, explaining the advantages and disadvantages. And that's all I got. Thank you very much.